let's say we have this charged object that is 6 coulombs, and we just put it at this location in space, and we measure the force on it. And we find that that force is, let's say, it experiences a force to the right, and the strength of that force is, let's say 24 coulombs, or 24 newtons, I should say. So a 6 coulomb positive charge experiences a force of 24 newtons. So that's an experiment we could do. We could place the charge there and measure the force it experiences. But let's say we take that away and put in a different charge. Let's say the new charge has charge only, let's say 2 coulombs instead. How much force would you expect that 2 coulomb charge to experience? Would you expect the same amount of force or more force or less force or what?
I would expect a less force.
Yeah. And specifically, how much less? What would you expect the strength of the force on that 2 coulomb charge to be?
Would it be 8 newtons?
Yeah, presumably so. If it's 1/3 as much charge, then I would expect 1/3 as much force. So presumably this is experiencing a force of only 8 newtons. And presumably what would be causing this force? Why would these charged particles be experiencing a force?
Is it a force due to the electric field?
Yeah, these are forces being caused by an electric field, which itself is probably caused by what? What would you expect to be creating that electric field?
The charge itself.
Which charge?
Like the positive charge.
Well, if a particle can't exert a force on itself, so this 6 coulomb charge has to be experiencing this 24 Newton force from something else. And the 2 coulomb charge would be experiencing a force from something else. Because forces are interaction between 2 or more objects. So ignoring the 2 coulomb charge for now, let's just take a look at the 6 coulomb charge. What could be exerting the 24 Newton force on that charged object? Where else could that force be coming from?
Coming from the +2.
Sorry, what was that?
It's coming from the +2 charge.
Not in this case. Let's ignore that +2 charge. Let's say the only thing we see in the universe is this positive 6 coulomb charge. And all we know is it's experiencing a 24 Newton force. Yeah, there's got to be some other charge, right? Maybe there's a positive charge for somewhere on the left. Like maybe there's some giant wall of charge over here. Maybe a wall of positive charge. And that's going to repel the positive charge. Or alternatively, we might have a wall of negative charge over on the left. Maybe we've got a big wall of positive charge on the left that's repelling it, or maybe we've got a big wall of negative charge on the right that's attracting it. We would call those the source charges. Source charges in the sense that they're creating some effect. And the 6 coulomb charge we would call the test charge in the sense that it's experiencing that effect. Specifically experiencing a force from that effect. And then the idea is this 2 coulomb charge, if we put it in the same place, we're not assuming these charges are interacting with each other. We're assuming they're both experiencing forces from some external source. So this 2 coulomb charge is also being maybe pushed away from the positive wall and or pulled towards the negative wall, but only with 1/3 as much force because it's only got 1/3 as much charge. Or maybe we could put a different charged object in the same place. Maybe we take the same location, but we place let's say a -3 coulomb charge. What would you expect the force on that from the walls to be?
It should be going to the left in the opposite direction of the 6 and 2 charge.
Opposite direction, and how strong?
It should be 3 or 8, 12 newtons.
Yeah, it's half as much charge as the original charge, 6 coulombs. So it should experience half as much force under the same circumstances. But yeah, opposite direction because it's the opposite kind of charge. And again, we're not assuming these are interacting with each other. We're assuming each one is in isolation, experiencing a force from these walls of charge nearby. So imagine you just put one of these test charges at this location at a time, and then remove it and put a different one in the same location. So these are all experiencing different forces. Even though they're all in the same circumstances, why are they experiencing different forces?
Well, for the 6 and 2 charge, is it because the force is dependent on the magnitude of the electric field and the charge itself? So they have different charge values?
Yeah, they have different charges and therefore they experience different forces. But what do we mean by electric field? What is the same about this object, this location for all three of these objects? What is meant by the electric field?
It's the same for all of them.
It should be the same, yeah. But how would we actually calculate that? If we wanted to know what is the electric field at this location, what does electric field mean? Yeah, the ratio of force over charge. These all have different forces because they have different charges. But if you look at the ratio, if we take a look at that ratio, force over charge, like for instance, for the original 6 Coulomb charge, force over charge would be what?
For Newton coulombs.
Yeah, 4 newtons per coulomb, and specifically in which direction? If we got force to the right and we're dividing by a positive charge,
It should also be to the right.
Yeah, the result is a vector to the right. What about for the 2 Coulomb charge? If you take force over charge, what do you get?
You also get 4, and it's also pointing to the right.
Yeah, still 4 newtons per coulomb to the right. And what about for this negative 3 Coulomb charge? If you got 12 newtons to the left divided by negative 3 coulombs, what do you get? Vector can't be negative though. Vectors don't have positive or negative signs. They just have direction.
It'd be 4, but in the other direction.
Exactly. A vector multiplied or divided by a negative scalar gives you a vector pointing in the opposite direction. So we'd still say the magnitude is 4 newtons per coulomb because magnitude is absolute value for vectors. And the direction would be opposite of the force. So that'll be to the right. So even though all these objects have different amounts of charge and are experiencing different amounts of force and even different directions of force, the ratio of force over charge is the same for all of them. And that's what electric field means. Electric field is this ratio of force over charge.
I'll ask a question.
Mm-hmm.
So if we weren't given the forces, but we did want to calculate the electric field,
mm-hmm.
Then is that when we would use KQ over R squared?
KQ over R squared tells you the electric field caused by a single point object, a single point source charge. In this case, is the electric field caused by a single point source.
So how would we determine the electric field in this situation if we weren't given the force?
Well, since the electric field is caused by a wall of charge, there's a separate formula for that. I forget exactly what it is, but it depends on the charge density, like how much charge per square meter.
Okay.
So it would be caused by the walls. You'd find the electric field contribution caused by each wall of charge and add those together to get the total electric field in the region. Okay. So each of these particles is getting a different amount of force because it's experiencing different, because it has different amounts of charge, but the ratio is the same for all of them. So electric field is just that ratio of how much force the particle experiences over how much charge the particle has. And that's the same no matter what the particle is. In fact, we generally consider the electric field a property of the location in space, even if there's no charge there at all. Even in the absence of a test charge, we'd say this location in space has an electric field of 4 newtons per coulomb to the right. So I generally think of the electric field as the capability of that location in space to create a force on a charged particle if there were one there. And the general relationship there is electric field equals Q times F. Or sorry, other way around. Electric field is force over charge, or force equals Q times electric field, where Q there is specifically the charge of the test object itself. So the way we usually think about this is that the source charge, whatever is creating the effect, like in this case, the walls of charge, the source charge or charges create an electric field at this location in space. And then you can think of the electric field as creating a force on the test object. And of course, what's really physically going on here is that the source charges are exerting a force on the test charges. But it's useful mathematically to add in this extra step of source charges create electric field, which is a vector, and electric field creates the force on the test object. Because once we find the electric field, we don't need to worry about the source charges at all anymore. We can just say there's this electric field of 4 newtons per coulomb to the right in this region, and we don't have to care what caused it. Maybe it was caused by a positive wall to the left. Maybe it was caused by a negative wall to the right, maybe a combination of both. We don't have to worry about the source charge. We can just say, this is the electric field in this region and work from there. Any questions on that so far? So we may as well just rename this E. The electric field in this region is 4 newtons per coulomb to the right. And we don't need to list that separately for each particle because it's a property of the location in space. But let's see if we can bring the idea of work into this, the idea of a transfer of energy. Each one of these objects is experiencing a force. So for instance, you might be just holding it in place by exerting the same force in the opposite direction. But what if you wanted to move the object? Like, let's say we want to take this 6 coulomb object and move it to the left. Because if you just let go, it's going to fall to the right. It's going to accelerate to the right because of the force. But let's say we wanted to move it to the left instead. Let's say we want to take this 6 coulomb charge and move it to a new location. So specifically, let's say we wanted to move it to a new location that is, let's say 5 meters away. That means you're moving at 5 meters. And how much force do you have to apply to it just to keep it moving at a constant speed? Because keep in mind, you do need to apply a force just to keep it moving at a constant speed. If you weren't applying a force, what would happen to this object?
Would it keep moving in the direction that it is?
Not necessarily, because I'm not saying if there was no force at all. I'm saying if you're not applying a force to it, but there's already a force from the electric field. If that was the only force, 24 newtons to the right, what's going to happen to the object?
Then it would keep moving 24 newtons to the right.
24 newtons isn't a speed, though. It's a force. What does a force cause an object to do?
Does it cause it to change its speed?
Yeah, to change the motion, to accelerate. So if we have this 24 Newton force and that's it, this object's going to accelerate to the right. If it's already moving to the right, it's going to get faster and faster. Or if it were moving to the left, it would get slower and slower, come to a stop and turn around. But we don't want that to happen. We want to move it at a steady pace to the left. So if you want this to just move at a steady pace to the left, how much force do you need to apply to allow it to move at a constant rate rather than accelerating? Or to put it in another way, if we want no acceleration, what should the total force be? Yeah, we want the total force to be 0, which means to make the total force 0, you have to apply how much force to it and in which direction.
Wait, sorry, can you explain why we want the force to be 0 again?
Largely just to prevent this from accelerating. If the force on this object is non-zero, if the total force is non-zero, the object is going to accelerate based on all of the Newton's second law stuff we saw in 7a. Newton's second law, the sum of the forces on the object equals mass times acceleration. If the sum of the forces is not 0, then the object's going to accelerate. So if we want the object to not accelerate, then we want the total force to be 0. Something greater than 24 newtons. The thing is, if you're pushing with more than 24 newtons, the total force is to the left. If there is a total force to the left, what's the object going to do? If you're pushing harder than 24 newtons to the left, what would happen to the object? Like, let's say you were pushing with a force of 25 newtons to the left. If you got 24 newtons to the right and 25 newtons to the left, the total force will be 1 newton to the left. And what happens to an object if it's experiencing a total force of 1 newton to the left? If we have the forces not canceling out, if we have a non-zero total force, then what's going to happen to the object?
Sorry, I accidentally drew. My Wi-Fi was being weird, not trying to fix it. You were cutting out a little bit though, so I missed a lot of.
I was saying if the forces don't cancel out, if we've got the 24 Newton electrical force to the right, and let's say you're also applying a larger force, let's say 25 newtons to the left. In that case, what would you expect to happen to this object?
So the net force would be 1 newton to the left.
Which means what's going to happen?
It would still accelerate.
Right. And if we don't want it to accelerate, what does the applied force have to be? If we want it to just move at a steady rate. If we want it to move to the left at a constant speed, what does the total force have to be in order to move at a constant velocity?
So if we want constant velocity, we would want 0 force. So we would just want to apply 24 newtons to the left.
Yeah. If your applied force is exactly 24 newtons to the left, then the total force will be 0. And total force being 0 means the object can move at a constant speed. The reason we want a constant speed is that way, what kind of energy is not relevant? What kind of energy doesn't change if this is moving at a constant speed?
Kinetic energy.
Right. So by making sure this is moving at a constant speed, we don't have to worry about kinetic energy. And this is useful because if you're applying a force as the object moves some distance, what do we call force times distance?
That would be work.
Yeah. And the work you're doing, force times distance, that's going to be Force, 24 newtons, distance 5 meters. So that's what, 120 joules? So by applying this 24 Newton force while the object moves 5 meters to the left, you're investing 120 joules of energy into it. That can't be kinetic energy because we're assuming this is moving at a constant speed. So what kind of energy is it?
So it'd be potential energy.
Right. We have invested 120 joules worth of change in potential energy in it. This object has gained 120 joules of potential energy. What if we tried doing the same thing to the 2 coulomb charge? If we move the 2 coulomb charge the same 5 meters to the left, in that case, we just need to apply 8 newtons of force to balance out the 8 newtons of electric force. So how much work would you be doing to that?
It would be 40.
Yeah. Because we'd have 8 newtons times 5 meters is 40 joules. So this differently charged object, it's moving the same distance, moving along the same path, but it only gains 40 joules of energy instead of 120 joules of energy. So why do these two objects have different changes in potential energy? Yeah, they're experiencing different forces. And why did they experience different forces in the first place?
Because of their charge.
Yeah. So we can make a very similar statement as we did to the electric field. We can say these test objects experience different changes in potential energy because they have different charges. But just like we did for force, we took a look at the ratio of force over charge. If we take a look at the ratio of change in energy over charge, what's the ratio of potential energy change over charge for each of these objects? For instance, for the 6 coulomb charge, if we take the change in potential energy divided by the charge, what do we get?
That one would be 20.
Yeah.
Oh, they have the same.
Energy.
Yeah.
Yeah, 120 joules over 6 coulombs is 20 joules per coulomb. Also, 40 joules over 2 coulombs is also 20 joules per coulomb. So they're experiencing the same ratio of change in potential energy over charge. And we call that ratio the potential or the voltage, usually written as delta V. So this is called the electric potential or the voltage. And the reason it's called voltage, that's just because it's measured in volts. Joules per coulomb is the same as volts. And this is in fact the same volts, the same units of measurement we saw for circuits in 7B. 1 volt means 1 joule per coulomb, just as an abbreviation. So the electric potential, not potential energy, but the electric potential is the ratio of potential energy over charge, in much the same way that electric field is the ratio of force per unit of charge. So you can think of electric field as the ratio of how much force a test object would experience at that location divided by the charge of the test object. You could think of voltage or potential as the ratio of potential energy over test charge. So in the same way that electric field is a property of the location in space that you can think of as that location's ability to cause a force on a charged object, you can think of potential or voltage as that location's ability to give potential energy to the object. Or if you're talking about a path from location to location, delta voltage is the ability to do work to the object. the ability to involve a change in potential energy. So from location to location, there can be a difference in voltage, and that's a property of the locations. Whereas change in potential energy is a property of the object as it moves from location to location. So we might say from this region in space to this region in space, the region to region, from location to location, there's a change in potential of plus 20 volts. But each object is experiencing its own change in potential energy equal to that change in voltage times the charge. Because if you solve this for potential energy, you get potential energy equals charge times voltage. So voltage could be thought of as a property of the location that you can multiply by any test charge to figure out the potential energy that object would have at that location. Again, we've got a property of the location times the charge of the test object, telling you a property of the test object. Any other questions on that so far?
No.
And one other thing, if we try this with the negative test charge, let's say we take this negative test charge and move it to the left. What would happen to the potential energy of the negative test charge as it moves to the left? If we take this negative test charge and we move that 5 meters to the left also. First of all, do you have to push on this to get it to move to the left? What would this negative charge do if we just put it there and let go? Are you able to hear me now?
Yeah, but it's in and out a little.
Okay. What would happen if you take this object, the negative 3 coulomb charge, put it there and just let it go?
It would move towards the positive charged wall.
Yeah. And not only move, it's going to accelerate, getting faster and faster. If you don't want it to accelerate, though, if you just want it to move at a constant speed, what do you have to do to it?
You would have to apply a force of 12 newtons in the opposite direction.
Right. Essentially, you need to hold it back. If it's going to accelerate to the left, but you don't want it to, you need to hold it back as it moves to prevent it from getting faster. So you need to apply a 12 Newton force to the right. So you've got your applied force of 12 newtons. But let's say we're still allowing it to move to the left. We're just holding it back to keep it from getting faster as it moves. In that case, you're applying a force against the distance. So what does that tell you about the amount of work done? Would you call that a positive amount of work or a negative amount of work?
A negative amount of work.
Yeah. If the force you're applying is opposite to the direction of travel, then that counts as a negative amount of work. You are removing energy from the system by holding it back. So that means that the object is losing energy, specifically losing potential energy. The change in potential energy on this object is negative force times distance will be 12 times 5, so negative 60 joules. So this negatively charged object, as it moves to the left, is losing potential energy. And we can even see that using the idea of Q times delta V. In general, change in potential energy, that is electrical potential energy, should be charge of the test object times delta voltage, delta potential. We saw earlier that the change in voltage from this location to this location is plus 20 volts. That is 20 joules per coulomb. So change in voltage plus 20 volts. But if we multiply that by a charge of -3 coulombs, what do we get?
-60.
Right. And coulombs times volts is joules. So that means this, even though we move the negatively charged object from lower voltage region to a higher voltage region, the voltage is increasing, but the potential energy is decreasing because of the negative multiplier. So for a negatively charged object, low voltage region means high potential energy, and higher voltage region means lower potential energy. Any questions on that so far?
Yeah. Would it be incorrect to look at the field lines from the positive charge wall, like the direction of the lines point? Wait, did the line voltage?
Do you mean the electric field lines or the equipotential lines?
Yeah, the electric field lines.
Yeah, let's take a look at those. Because we saw earlier that the electric field is 4 newtons per coulomb to the right. And the thing is, the electric field is a property of the location in space. So even if we remove all of the charged objects, all the test charges here, if we just get rid of all these test charges, even in the absence of any test charges at all, we could still say these walls are creating an electric field of 4 newtons per coulomb to the right. And assuming that these walls of charge are very large and not too far apart, we can assume the electric field is constant in between, a uniform electric field that is the same value everywhere. So the way we would typically draw that out is field lines that are just horizontal and equally spaced. So we've got a 4 Newton per coulomb electric field uniform to the right. So the electric field lines would just look like this. And note that those field lines are pointing from the positive plate towards the negative plate. And the same magnitude everywhere, so we should expect them to be equally spaced. If we want to draw out the equipotential lines, though, an equipotential line is a curve that you can travel on that doesn't change your voltage. Let's say you're starting at a certain location. Let's say this location right here. If you travel to the right, what would you expect to happen to your voltage?
Your voltage would decrease.
Yeah. We saw earlier that moving to the left 5 meters means increasing voltage by 20 volts. Moving to the right would involve decreasing voltage. So the right side towards the negatively charged wall should be a lower voltage. Whereas if you move to the left, we should expect increased voltage. So the wall of positive charge, or near the wall of positive charge, is a higher voltage region. Near the wall of negative charge is a lower voltage region.
So the field always points in the direction of decreasing voltage.
Exactly. In fact, that's what's meant by the equation that relates them together, that electric field is negative derivative of voltage with respect to position. This is just saying that the strength of the electric field is how fast voltage is changing, not per unit of time, but per unit of distance. So for instance, if we're saying the electric field is 4 newtons per coulomb, we're saying that the voltage changes by 4 volts every meter. In fact, that's another way you can write newtons per coulomb. Newtons per coulomb is the same as volts per meter. So volts per meter is often a much more useful way of thinking of electric field. 4 volts per meter means every meter you travel, the voltage changes by 4 volts. So maybe right here, the voltage is 10 volts. Move 1 meter down the line, and you've got an additional 4 volts or 4 volts less, depending on the direction. So 1 meter away from 4 volts would be 14 volts in one direction or 6 volts in the other direction as the final voltage. So that's really the main idea of how electric field is related to voltage. The strength of the electric field tells you how much the voltage changes per meter. And the direction of the electric field always points towards lower voltage, which is what's meant by this negative sign. That is, the electric field is pointing in the direction of decreasing voltage. So if you travel along the electric field, you're traveling towards a lower voltage region. If you travel against the electric field, you're traveling towards a higher voltage region. But what if you want to keep the same voltage? Like let's say you're at this location and you want to travel in some direction that doesn't change your voltage. Which direction could you travel that doesn't change your voltage at all?
You can go like vertical.
Yeah, if you travel vertical, exactly perpendicular to the electric field lines, you're not traveling with the electric field, so your voltage doesn't decrease. You're not traveling against the electric field, so your voltage doesn't decrease. As long as you're traveling exactly perpendicular to the electric field, that path involves no change in voltage. So we call that path an equipotential line. Equipotential in the sense of same voltage everywhere, same potential. So traveling along this path involves no change in voltage. You could also think of that as a path that involves no work. If you take a charged object, it has a certain voltage, right? It's at a location with a certain voltage. If you move it along that path, there's no change to the voltage and therefore no change to the potential energy. So moving an object along an equipotential path is free in the sense that it doesn't require any work. Whereas if you move it with the electric field or against the electric field, you have to either add or remove energy. But moving it along an equipotential line involves no change in potential energy at all. So that means it is free. It does not require any work one way or the other. So this particular path is associated with a certain voltage. And for convenience, it's often useful to call a point in the middle 0 volts. Let's say this location is marked as 0 volts, just as a convenient reference point by convention. But let's say you move 1 meter to the right. If you move 1 meter to the right, so now you're at this location, what would be the voltage at this new location, 1 meter further to the right? What should we expect to happen to the voltage if we're moving along the electric field?
Sorry, you cut out. Did you say what would you expect to happen to move?
What would happen to the voltage if you're moving along the electric field?
Decrease.
Yeah, we'd expect a lower voltage if you're moving to the right. And yeah, if we call the voltage in the center as 0 volts, then moving to the right decreases the voltage. So we now have a negative voltage. And if you're specifically 1 meter away, the electric field being 4 means 4 volts per meter. So moving 1 meter away means you lose 4 volts. You're now at a voltage of negative 4 volts. And the equipotential line here is still going to be a vertical line. Because if you move up or down perpendicular to the electric field, the voltage doesn't change. So the equipotential line is going to be a vertical line, and every point on this vertical line has a voltage of negative 4. Or if you move another 1 meter further to the right, we'll get another equipotential line, still 1 meter spaced away from that. 1 meter further to the right is going to be another 4 volts lower. So that's now going to be at negative 8 volts. And then negative 12, negative 16, getting lower and lower voltage as we get closer and closer to the negative wall. On the other hand, what would happen to the voltage if we move to the left? Yeah, if we move to the left, we would get an increase in voltage. So 1 meter to the left of the center would be 4 volts higher than 0. So that would be positive 4 volts. And then another 1 meter further to the left would presumably be 4 volts higher than that. So another 1 meter equally spaced is going to be positive 8 volts, and so on. So by drawing out the equipotential curves, and these are usually spaced by voltage, like maybe we draw an equipotential curve every 4 volts or every 10 volts or every however many volts. That's essentially a map of the voltage everywhere. So anywhere on this line, this curve here is at 4 volts. Anywhere between 4 and 0 is somewhere between 4 volts and 0 volts. But the nice thing about having a map like this is it means you can figure out changes in energy from a location to location much more easily. For example, let's say we take a charged object here, and let's say we know its charge. Let's say the charge of this object is -5 coulombs. And let's say we move it to a new location that is here. Maybe along some weird path. Let's say we move it along a path like this. To its final location here. So this represents the path of motion. As we move it along this path, presumably its energy is changing. We can figure out the change in energy though, if we want to know the change in energy, change in potential energy. How would we calculate the change in potential energy of this object as it moves along this path?
We would look at the final voltage and initial voltage.
Yeah, all we need to care about is final and initial. Any delta doesn't really care about the path, it just cares about the initial and final points. So we can take the change in voltage. Specifically, we can say the change in voltage, final minus initial. What's the final voltage and what's the initial voltage?
Final would be -4 and initial would be 8.
Yeah. So if we subtract those, we get -4 minus 8 would be -12 volts. So from start to finish, the overall change in voltage or potential is -12 volts. How do we convert that to change in potential energy?
So it would be the charge times the change in voltage.
Right. And we know the charge here is -5 coulombs. Multiply that by the change in voltage, -12 volts. And what do we get?
60.
Yeah, specifically positive 60. And volts is joules per coulomb, so volts times coulombs is just joules. That means as this particle moves, ignoring what happens in between, just looking at initial and final, we can say that it has moved to a lower voltage zone, but it's negatively charged, so that means it gains potential energy. Specifically, it has overall gained plus 60 joules of potential energy. And note that we don't have to care about the path here. We don't have to worry about the weird interactions between force and distance and angle. For change in potential energy overall, we just need to care about initial location voltage and final location voltage. Take the difference in voltage, multiply by charge of the test object, and that tells you the overall change in potential energy. Any other questions on that?
Yeah, I have a quick question about potential energy.
Mm-hmm.
I think our TA and DL told us that nature always favors decreasing potential energy.
In a way, yeah. And it's really more a statement about force. And this is related to what we, not just related, this is exactly what we saw in Physics 7a. that every potential energy is associated with a force, and force is specifically negative change in potential energy over change in position. Force is the negative derivative of potential energy. So this is essentially saying that the strength of the force is how much the potential energy changes per meter. The direction of the force, this negative sign, tells you the direction of the force is in the direction of decreasing potential energy. For example, let's say force of gravity. Which direction is the force of gravity point? In general, if you've got an object with mass, which direction is gravity pulling it? Usually, which direction do objects fall?
Sorry, you cut out again, but I got the last part. So objects fall downwards.
Yeah, force of gravity pulls objects downwards. And what happens to an object's potential energy as it moves downwards?
Oh, it decreases.
Right. So the force of gravity pulls down. It's pulling from a high potential energy zone towards a lower potential energy zone. Same thing with a spring. No matter whether a spring is stretched or compressed, the spring is pushing or pulling back towards equilibrium, which is the lowest potential energy location. So in general, any force that's associated with a potential energy is a force that's going to be pushing or pulling towards lower potential energy. And this is exactly equivalent to this other relationship between electric field and voltage. Because to convert force to electric field, you divide by charge. To convert potential energy to voltage, you divide by charge. So if you just take this equation with force and potential energy and divide both sides by charge, it turns into an equation with electric field and voltage. Same structure of the equation, just different meanings of the variables. We've divided both sides by charge to get this. But it's effectively the same meaning. Any other questions on that?
No.
All right. Then I will see you next time.
Yeah.